All right, thank you very much for coming. This talk is going to be a little bit nonsense, so please bear in mind that this is like partially technical and partially nonsense. Okay, so the title today is A Beginner's Guide to Deep Natural Language Processing with PyTorch. By the way, if I'm speaking with this speed, is this okay for everybody to catch my words? Okay, so it's just a statement. Okay, by the way, I've got a slide for my kind introduction. My name is Arm, so you can call me Arm. You can find me on Facebook. I'm very active on that. And I'm a researcher at NECTech. I've been doing that kind of job since 2005. And now it's been 12 years working on NLP. So yeah, it's been quite a long time since I was graduated from University of Edinburgh. In computational linguistics. So I've got some background in that. But today I'll be talking about more technical details about deep learning and how to apply that to natural language processing. This is the QR code to my slide. So if you're interested, you can scan the QR code here. You can walk to the front and scan it. Otherwise, you can just follow the URL down here. So that's the outline of my talk. It's going to take a little while. I'm not so sure if I can cover in 40 minutes or not, but I'll try to wrap it up. Okay, so first of all, introduction. Okay, welcome, welcome. Hi guys, welcome. Okay, so introduction. Everybody has been talking about deep learning ever since. It's been here. It's been in the academia since mid-2000s. And deep learning helps a lot, helps improve the accuracy of traditional natural language processing methods. Back in the day, they used statistics for prediction, or like in machine learning terms, we call it classification problems and clustering problems. But now they're applying deep learning to boost up the accuracy. And there are some notable examples, like AlphaGo. You may have heard about it already. AlphaGo, the deep learning, outperforms the Go players, like the world champions. And also Tesla. Tesla is a self-driving car. It used imitation learning, a kind of reinforcement learning for training for driving from experts. So it imitates the experts' capability of driving. And maybe racing too. I don't know. I've heard about some accidents, like road accidents, caused by the Tesla. And the last one, natural language processing, like Siri. You may have a fight with Siri all the time. Yep, it's been on a fight ever since it was released a few years back then. It's also based on deep learning, like speech processing and stuff like that. And for today, I'll be talking about a library called PyTorch. PyTorch is developed by Facebook for machine learning and tensor and matrix computation. It is really good. It is really flexible, and it has some abstraction. It provides an abstraction for building blocks of deep learning. So don't worry about the abstraction. I'll be talking about that, and I'll be elaborating everything about it. It has a very gentle learning curve, so don't worry about learning with PyTorch. You will see that in my talk here, how easy it is to learn it from scratch. And it has some capability for dynamic network architectures. So in the literature, people use static network, like they use fixed shape networks for classification and clustering. But for PyTorch, it enables you to use dynamic network architectures. It unleashed the power of dynamic networks. And it is really easy to debug. I'm a bug originator, basically. I always cause bugs in my code. And it's really hard. It's a pain in the ass to use TensorFlow because you cannot print out the result at that time. It's so confusing. It's so irritating. So I moved to PyTorch back then. And last but not least, it has a very well-written documentation. If you take a look at TensorFlow and Keras, you will see that the documentation is kind of poor. But for PyTorch, it's the other way around. Everything is good. Everything is well written. And you can take a look at that on the website. For installation, it's really easy. You can install it with Conda. So Conda, install PyTorch and Torch Vision, stuff like that. Go to the website, pytorch.org, for the instruction. And you can also use that on Windows. If you have a Windows laptop, you can run it straight away. And it makes use all the CPUs and the GPU cards available on your laptop. So feel free to do that. It's really easy to use. Once you install that, you can try it out by yourself. Like, for example, this is an example code, an example piece of code. So you can import Torch from the library. Once you install that, import Torch as T. I'm using T as the acronym for that. And you can create a zero matrix with the command zeros and ones for one matrix, and the identity matrix for the identity matrix. It's basically NumPy on GPU. So if you're used to NumPy, it won't be difficult for you to move to PyTorch. And you can also do the matrix computation, like addition and multiplication. Scalar multiplication in this case is really easy to use. Okay, this is the QR code for my slide. So if you just arrived at my talk, that's the QR code. You can scan it, and I'll be repeating that all the time as I change the section. So the basic idea of deep learning. The basic idea of deep learning, it's really complicated at first, but it's actually very easy. So it's actually, let's go back to our biology class back in the day. It gives me goosebumps all the time when I talk about biology. But anyway, one of the subjects that has been taught a lot in biology is the brain cell. We call it neuron. So the neuron consists of two major components. The first one is the nucleus, which has some dendrites. It's an antenna, like it has antenna receiving this incoming signals, and it processes the signal and send the output signal through the axonal fiber right there to other neurons. So that's the way the neuron cell communicate to each other. We can imitate that. We can simulate the brain cell using mathematics. This is the simulation of that. We call it perceptron. So basically, you've got the input signal. You multiply each input signal with the weight of each connection, like the first one with a 0.2, 0.3, and 0.5 respectively. And you sum them. You add them to get the addition, 0.7. And you screen the output signal with the activation function. For example, I'm using that activation function, which fires an output signal if the input signal is more than 0.5. So it fires 1 as the output signal. That's the basic idea of neural network, perceptron. If you compose all perceptrons into layers, so you've got the input layers, and the next one is the hidden layer as a classifier. The hidden layer compress the input signals into patterns. So if you want to take a look at the patterns, underlying patterns, the hidden layer will do that for you. It compresses the dimensions of the input signal into patterns of features. And it fires the output to the output layer. So that's the basic idea of that multiple layer perceptron, or MLP. It's not NLP, it's MLP right here. But if you add more hidden layers into the network, so you can gain, for example, you can achieve like many multiple hidden layers in your network, and it's become deep neural network. That's the definition of that. If you have more than one hidden layer, then it's a deep neural network. And that's the deep learning we are talking about right here, right now. By the way, as I aforementioned, the more you can learn the patterns, the underlying patterns of the data by hidden layers. If you add even more and more hidden layers, the patterns become more abstract. So the more layers, the more abstract the representation you can learn from the data. Therefore, higher accuracy. Let's take a look at some example of the deep learning. So this is the network for classifying the sex, the gender of the picture. Like if it's a male or a female, for example, or some other genders, neutral maybe. But now we are talking about two genders, male and female. And it accepts the each pixel from the picture and as an input feature. So you've got 3 hidden layers here. The first layers will learn splotch, like patterns of dark spots and light spots, for example. But the next hidden layer learns more from that, more from the splotch. So you can gain the eyes, the nose, the mouth, the lips, for example. And the next layer, the third hidden layer, will learn from that eyes, nose, and patterns like that. It composes into a face. So you've got a face. That's how we tap it with heat mapped. And then you can classify the genders from the face shape. Right here, right now, if we are talking about a model, it's actually the weight of each connection between each nodes in there, between each perceptrons in here. How we train it, how we adjust the weight. We use the backpropagation algorithm. So basically, when you feed forward the input features, input signal, into the network, it will produce something, some signals like 0.25 and 0.75. But you've got a training data. So you've got to compare the training data and the output signal. Once you compare them, you're going to get the error. This is the square errors. So basically, you compute the difference between the 2 signals, and then you square them, and then you summation them, so you get the errors. And then you use the errors to adjust the weight, to minimize the errors. So in a nutshell, we use stochastic gradient descent to adjust the weight. So that's the curve for error over there. We adjust the weight bit by bit, starting from a random point. So we adjust the weight by considering the slope of the graph. If the slope is very, very shallow, you can go slow, but if it's very deep, you must go fast. So it goes like that. That's the way we adjust the parameters. We call it estimation. Okay, so far so good. That's the theoretical part, which is nonsense. Okay, let's take a look at the code. This is the fun part. Okay, let's implement something with PyTorch. So your first network is XOR, exclusive OR. We're going to imitate the exclusive OR gate with the neural network. We're going to train it with 1,000 samples and test it with 100 samples. Very, very easy. If you have not heard about the exclusive OR, it's basically considering 2 input signals. If one of them is 1, then it results in 1. Otherwise, it results in 0. So far, so good. It's from digital design. Back in the day, I've got B+ for that, fuck's sake. Okay, so the code header for PyTorch looks like this. So you can import the torch as T. This is my favorite imports. Torch as T, torch.nn, neural network, as N. Because I don't want to type a lot. So I use acronyms all the time. Torch.nn with N, and torch.optimizer as O. So from now on, I'm gonna refer to Torch as T, neural network as N, and optimizer as O. And I also recommend 2 more libraries for you. TQDM, that's for progress bar. It's really good, it's really beautiful. You've got to take a look at it. And matplotlib for plotting the graph. So let's take a look at the network. The network goes like this. We're going to employ the multiple layer perceptron, or MLP, for the XOR. To implement it, it looks like that. So you add 2 layers, 2 linear layers into it. The first one has 2 dimensions, two input features and 8 hidden perceptrons. So you define that with the first line, n linear. And the second one, that's the transformation from the hidden layer into the output layer. So it goes like that. But symbolically, we prefer to draw the diagram, which look like that. Very easy. 2 linear layers with the linear with 8 for dimension and 1 for the dimension as well. So far, so good. We're going to use a diagram. This is how we generate the training data. We generate 1,000 samples with 3 components. A and B is the input signal, and Q is the result from XOR. And also the testing data. So we generate A, B, and Q, where Q is the exclusive OR of A and B. That's the testing data. So we generate a set for training and a set for testing. This is how we train it. It looks complicated at first, but let me decompose that for you. Okay, so for each instance, first, we convert the training data, which is like A, B, and Q, into 2 vectors. X is for the input, and Y is for the output. And then we convert that from true and false into 1 and 0. So that's the first part. Second, we feed X into the model and get the prediction. Third, we calculate the loss between the output and the training data. And last but not least, we do backpropagation with the loss and tune up the parameters. So we repeat that over and over again for the number of epochs you want to do. I set number of epochs for 40, so that's going to be it. And we also keep track of the loss function. So we plot the loss history for that model, which looks very, very convincing. The loss function goes downhill. But if you take a look at the Y scale, that's not very wide. This is just from 0.26 to 0.25. That's the loss you can decrease, which is like unsatisfactory. Okay, so far so good. And this is how we test it. We convert the testing data into a vector, and then we feed that input vector into the model, and we get the prediction, and then we compare the prediction with the testing data, if it's correct or not. And we report the accuracy. So from now on, let's guess how much accuracy we can get from that model. Let's make a guess. How much? Anybody, any idea? 100? Any more numbers? Any numbers? 42. Oh, okay, 42. That's the universe. That's the universe answers. That's the answers for everything. Universal answer. Any other numbers? 50. Very close. So the accuracy for that model, that excuse me for the audience back home, excuse me my words, it's fucking low. That's 56%. That's very, very low. You cannot come up with the random neural network and train it with the data and hope it's to work. No, it's not like that. There's a lot more to explore in deep learning. The model looks convincing, but it's actually a sad face. So let's take a look what's going on here. So let me introduce something into the model. We call it Sigmoid Function. Sigmoid Function means something in Thai, so I'm not going to say that. Okay, I'm sorry, but that's me. They forced me to just sit down. Actually, I just run around in the room and give a talk. But now I'm like sitting here, stationary. Okay, by the way, I can be joking around. Okay, so I add the Sigmoid Function in between, like after the hidden layer. The Sigmoid Function down there. And let's see what's going on. So I train it again, and I achieve 100% of accuracy right away. What's going on here? I just add one activation function, and it works perfectly. That's strange. So based on the literature, the moral of the story is the activation functions actually narrow down the input range of the hidden layer. Therefore, faster convergence, if you take a look at the loss function in the plot, it converges very, very fast. Within 25 iterations, it converges and stops right there. And also higher accuracy. So it means that if you can scope down the input signal for each layer, you can actually train a lot faster. That's strange. There are a lot more nonlinear activation functions, like sigmoid or hyperbolic tangent. I stressed that syllable for a purpose. Sorry. Okay, and hyperbolic tangent, which is faster. That's my favorite one, my favorite choice all the time. But for image processing, it's rectified linear unit, or ReLU. It allows only the positive signal to pass through. That's rectifiers in electrical engineering, basically diode. So you added a diode into your network. So if you're working on image processing, ReLU is your choice, almost always. Not only that, once you've got a perfect model for your work, you can also convert that. You can modularize your model into a class, which look like this. You just extend the n.module, and then you just define the layers, and then you define the method function called forward for computing the output vector. Just that. Very, very easy. And you can print out the result every fucking time once you've got a bug. You can print out out1, out2, and out3 along the way when you debug it. You cannot do that on TensorFlow, right? I'm not having a fight with the TensorFlow guys. Okay. Okay, this is how we apply that to deep learning for NLP. So first of all, when we're talking about natural language processing, we're talking about linguistics, basically. You've got to have some background in linguistics. But for this talk, you don't. You don't have to. Okay, I'll be talking a little bit about that. In linguistics, we are talking about hierarchical structures, like from characters to syllable, from syllable to words, from words to phrase, from phrase to multiple word expression, stuff like that, into phrase, into sentence, stuff like that. We can interpret that with deep learning. We can also represent that and learn that automatically from the data. So the first topic will be representing linguistic units in deep learning, especially in PyTorch. I'm staring at the camera all the time because I've been the TV host, so I'm used to the camera. I'm not kidding about that. Okay, so first of all, in natural language processing, you need to deal with the vector of elementary units. You can think about the characters, you can think about the words, you can think about the phrase, you can think about multiple word expressions, stuff like that. But for that, you've got to map them into a vector called embedding vector. To do that, you just declare an embedding layer. It's so straightforward. Just declare an embedding layer, like n.embedding, and then you declare, you just add the parameters of the number of characters or the number of units you want and the dimension of the vector that you want. And based on that, once you've got a series of characters or the linguistic unit that you're talking about, like CUTER, that's the characters. So basically, you index them, each of them, with the numbers, and then you pass it through the embedding layer. So you've got a matrix containing the embedding vectors for each element. The X means the embedding vector for each element. Next thing, recurrent neural network. Because in natural language processing, you've got to learn about the context. Like you cannot consider how to classify things based on the single object. You've got to learn that from the context, like previous context, stuff like that. And in deep learning, we use recurrent neural network to do that. For example, if you take a look at the diagram on the right, it's the hidden vector H passed to the next input. So as you pass the hidden vector to the next input, x2, from x1 to x2, you're actually remembering the past. You can remember the past temporarily based on the recurrent neural network. There are several gates for RNN, or recurrent neural network, like GRU, gated recurrent unit, or long short-term memory, LSTM. But for my favorite part, I'm using GRU because it has one less gate and faster training time. We pass the character vectors, the matrix of the character vectors, into the GRU, and it learns that automatically. You're going to get two things, these context vectors and the last hidden vectors. We don't care about the second one. We care about the context vectors. So we just take that and squeeze. We remove all the dimension having only one element from that matrix. It is, the output is actually a tensor, but we've got to delete that empty element out. So we just use the command squeeze. I always do that. Once you've got that, you can also learn the context on both sides. We call it bidirectional RNN. So to do that, you add one more flag. Bidirectional equals true. Just that, very, very easy. You don't have to deal with it yourself. Really easy. But the thing is, the dimension of the output vector becomes twice the dimension of the transition, the hidden vector. So you've got to bear in mind about that. But don't worry, it is documented very well in the documentation. So just don't care about it at the moment. Next, if we add more layers, more recurrent neural network, RNN layers, you can actually learn more abstract representation, just like the image processing. If you use one layer, you're going to learn a syllable. You can learn a syllable because it composed of multiple characters. But if you add one more layers, you're going to learn the morpheme, which contains more than one syllable at a time. And if you add even one more layer, you can now learn a word. So the more layers, the merrier. But not always the case, because you've got to train that for a long, long time. But that doesn't work that way. OK, so you've got to find out the optimal number of layers for your work. For this case, I'm using 2 layers of RNN right here. And diagrammically, I represent the network over there with this simple diagram, like embedding for the first layer, and n times bidirectional GRU. Very easy to remember. You cannot miss that. And it is equivalent to 2 lines of code with that diagram. If you take a look at the first line, first 2 lines, that's actually the diagram for it. So it's really easy to take a look at the the model, and debug it from scratch. Next, once you can learn about the linguistic representation, you can also make a prediction. And in this case, I'm using a very, very simple case of prediction. We call it sequence prediction. This is taken from my NLP class last semester. So it's a little bit tedious. I know. I'm sorry for that. I can make it even more interesting in that. OK. Anyway, sequence prediction. We are going to predict what's going on underneath the given string. We assume that for a given string, it is statically generated by a hidden sequence of state transition, like that one. So you've got 3 hidden states, and from the starting state, it moves from one to another, and as it moves, it generates a symbol. It looks very tedious. That's actually hidden Markov model if you have some background in statistics. This is hidden Markov model. You can apply that on many natural language processing tasks, like part-of-speech tagging, finding the grammatical function of each word, like what is the noun, what is the verb, what is the adjective, stuff like that. If you take a look at the diagram, the first step is the adjective, and it generates big. And the next one, dog generated from noun, and Che generated from verb, stuff like that. In sequence prediction, we have a string, big dog, chase small cats, as an input. And then we predict the sequence of the hidden states. Also, That's the way we do it. And also name entity recognition. We are predicting the sequence of the phrase or names boundaries. Like B is the begin, I is the intermediate, and O is for outer, stuff like that. So you've got IBM Watson prescribe me Tylenol, which is a joke, because IBM Watson is for hospital management, and it prescribes you a Tylenol, just a paracetamol pill for painkiller, which is like nonsense. I told you that's nonsense. Okay, the last one, word segmentation. You can also predict the word boundaries by sequence prediction, because there is a state transition of true and false, where true is for segment at that point, and false is for not segmenting at that point. So from here, you've got the sentence like tam ha, follow to track, and you segment at the third characters. Okay, stuff like that. So we're going to use the word segmentation as an example here. We assume that we can learn the abstract representation of words by multiple layers of RNN. So we use the RNN. So basically, you've got two first layers, embedding, and the bidirectional GRU. As many layers as you want for the bidirectional GRU. And we add an activation function called hyperbolic tangent. That's my favorite activation function. You can change it to anything you want. It works too. Okay. And I add the hidden layer as a final layer for predicting the boundaries. So you've got that model. But the problem is the resulting vectors, S, for selecting the boundaries, is not a probability distribution. The thing is, the range of each element in that vector can vary from -infinity to +infinity, which is very, very hard to train. Can we scope it down to something like a probability distribution, like from 0 to 1? Yes, we can do that. We use Softmax Distribution. The Softmax Distribution is a popular method for translating a non-probabilistic vector into a probabilistic distribution. Like for any element of that, the result, J, it is actually a normalized exponential of that value, of the input value. For example, if you take a look at the diagram on the right, so you've got the values which is not probabilistic at all, because it contains minus, and some of the values are more than 1. We want something between 1 and 0. Sorry, 1 and 0, yes. So we just compute the exponential of each value and normalize them to get the probability, just like that one. Very, very easy. We call this one softmax distribution. It is always used, almost always used as a posterior probability in classification problems, like word segmentation and stuff like that. So we're going to use that as the final layer here. So this is the way we implement the word segmentation. So we declare the embedding layer and number of bidirectional GRU as the second line. And the third line, we declare the hyperbolic tangent function. And the next one, hidden layer. And the last one, the softmax. And the way we compute that, we just follow through the standard practice. So we just input the character vectors into the GRU and squeeze it to get the matrix of the resulting vectors. And for the state vectors, we apply the hyperbolic tangent first. It's from inside out. Okay, so we begin with the hyperbolic tangent, and then we apply the hidden layer, and then we apply the softmax as in the final step. So that's the way we can get the resulting vectors, S. We can also implement that as a class. We can modularize it. So we just define each. Don't worry, I can finish on time, don't worry. I've got 10 more minutes. We have plenty of time for question and answerings. Okay, okay, I enjoy question answering. Okay, and in the initializer, so we declare the layers based on the diagram, just like that. And for the forwards, we just input the character sequence. Then we just convert that into a long tensor, and then we just pass it through the GRU, and then we squeeze them, and then we apply the hyperbolic tangent on the context vectors, resulting context vectors, and then the hidden layer. And finally, we apply the softmax to make it probabilistic. That's the way we do it. And this is the actual code of NetTech word segmentation module. This is the actual code of that. Very, very simple. Yeah, it's online already. But I'm not making it a commercial here, okay? I'm not promoting my own work. So let's take it offline if you want to use it. We are available for licensing. Okay, and one more thing to add. When you're working on deep learning, sometimes when you train the model, it becomes data overfitting. Data overfitting is the very, very serious problem in deep learning because that effect, that phenomenon, we call it co-adaptation. In co-adaptation, some perceptrons become lazy. Like if you've got a friend who's good at everything, it learns a lot from the data. And you say, he's learning a lot. I don't have to work on myself. I can just rely on him all the time. And that happens in perceptrons when you train the deep learning. Co-adaptation is a very, very serious problem, and it causes data overfitting all the time. So to do that, we can simulate the brain damage. Yep, let's take it. Let's make an analogy for that. This is the dropout. Dropout is a simulated brain damage. So basically, if something learns very good, it outperforms the others, so everybody else is lazy. So let's kill him first. Let's kill that diligent guy first, and let the others learn from the data. That's the basic idea of dropout. So you randomly pick some perceptrons in the network, and then you drop them out and train the model like normal. Once you do that, you're gonna force the rest of the pack to learn something from the data and adjust the parameters along the way. By doing that, when we eliminate some diligent students from the class, you've got lazy students to learn. That's the way we force them to learn. And it solved the data overfitting problem straight away. As a standard practice, we ignore about 20% of the units in each layer when training, and it works perfectly. I highly recommend that in your networks. How to add that into your network? That's a problem. To do that, you just add one more parameters in the DRU, dropout equals 0.2, to allow dropout during training. It's really easy, right? Really easy. If you want to modify the model, you just add some more dropout. You can increase the dropout rate, stuff like that. It's always the case for you. It's really easy. Last but not least, training. When we train it, we've got to have a data, like a data set for training the word segmentation. And it's really easy. So the thing is, for each instance for training the word segmentation, you've got to have a sequence of characters. That's the first thing. The next thing, you've got to have a sequence of the same length, identifying each position if it's the boundary or not. If it's a boundary, it's true, otherwise it's false. And then you feed forward them into the training model. It's basically the same. Once you've got the character sequence, you pass that to the model. When you've got the segmentation boundaries, you convert that into an output signal for predicting the boundaries. And then you do the standard practice for training. You compute the prediction, you compute the loss from the loss function, and then you optimize the parameters with the loss. So far, so good. It's really easy. And this is the actual code of word segmentation module of NetTech. This is the actual code. Okay, so far, so good. I'm making a good timing. So this is a conclusion. Okay, we can jump to the lunch like before time, which is, fuck, yes. Okay, conclusion. I've been talking about PyTorch. If you're using TensorFlow or Keras, it's a pain in the ass to debug your code because sometimes it crashes by matrix multiplication. And it's really hard to debug. With PyTorch, it's a lot easier. You just print out the step that causes bugs. And it tells you right away, like which step has a wrong dimension mismatch, something like that. If it's mismatch, it's just stop there and let you correct the code. It provides flexible routines for matrix and tensor computation. So if you're into like hardcore deep learning, like you do the math yourself, you can also use PyTorch, just like TensorFlow, but a lot easier because you can debug it. And it has some abstraction for building blocks of deep learning. I'll show you in the next slide how many building blocks you can use with PyTorch. And it has a very gentle learning curve. You have learned everything about deep word segmentation of NeckTech from my code. So it has a very gentle learning curve. It's capable of dynamic network architectures. I'll show you in 2 more slides after this, like how to create a dynamic network architectures. And it's really fast. It's really fast, believe me. And it has a very well-written documentation. You don't have to get in hell to dig up the documentation, like from a few years back then in Keras or TensorFlow. Everything is written very perfectly. OK, here is the building blocks for deep learning. You can take a photo of this one if you want. So there are about 8 layers for deep learning here. Linear transformation, nonlinear, and embedding layers for sparse items. And also recurrent neural network, RNN, which has GRU or LSTM. You can also add a dropout layer if you want. It has a dropout layer for it. And it's capable of doing convolutional neural network or CNN. If you're working on image processing, you can also use PyTorch. And there will be a talk on that tomorrow, so don't miss it, by one of my friends. CNN, it extracts local features from the picture. Like you are detecting a gun in the pictures. You're using CNN to detect the gun specifically. Stuff like that. And you can also do feature pooling, like selecting the most prominent local features out of the convolutional neural network, stuff like that. And you can also add more activation function, like sigmoid, hyperbolic tangent, ReLU, softmax, stuff like that. There's a lot more in the collection. And there's also loss function, like negative log loss, binary cross-entropy loss, and cross-entropy loss. There's a lot of things to do with it. Have fun trying it out. And the last one, recursive neural network. This is dynamic network. So you've got a tree. You can also create a network based on that tree. So for each node, you're going to have a cost or the constituency cost and a vector embedded to each node. And you can compute the vector of the parent node by the following network. And it cannot be implemented by Keras. You have to use something that allows you to use dynamic networks. So you have to resort to TensorFlow. Or you can still use PyTorch in here. It's really easy, like 4 lines of code for that. So for that, just use it. And that's all for my talk. Thank you very much. Good time. Okay, that's great.
Thank you very much, Kun Prachya. I think we have time for one question.
One question? Just that? Oh, one question. Boo.
I have a quick question there.
Yes,
I think
please.
PyTorch is pretty easy, look promising. One quick question I have would be when you train a very large neural network, right?
Right.
TensorFlow, you can train on the cloud. You have cloud ML that you can do the
Right.
training.
That's
How
correct.
about PyTorch though?
Okay, I've got to speak about 2 topics here, memory usage and the training time. For the training time, I think it's lower, a little bit slower than TensorFlow. But for memory usage, it's a lot more optimal.
But if you have something that you cannot do on one machine,
Right.
and you want to distribute into multiple
Ah.
things. How do you do that on PyTorch?
You can also do that on distribute network. It allows you to actually train the model on distributed networks. Like
Okay.
you can assign these GPU servers and these GPU servers, stuff like that, to collaborate in training.
Okay, thank you.
So it's actually practical. It's developed by Facebook, so somehow it's optimized for that, for the cloud computing. Can we have some more time for one more
Sorry,
question?
yes, time up.
Oh, the time is up. Boo.
So we will have a 10 minutes break after this. So thank you again, Mr. Prachya.
Okay, thank you very much for coming.